damped oscillation. So what do I mean by damped oscillation? Okay. Basically, when you've got a system that's oscillating in real life, there's going to be energy that's disappearing from the system. Okay. And that energy, either we want that energy to disappear, or we want, that energy is quite obviously, things won't oscillate forever because we're, natural world. Things are going to reduce. We can do lots of things to try and make them as free oscillating as possible, but eventually things will stop moving, okay, because of damping. Now, obviously, in an automotive application, the thing that you might think when somebody says, what's a damper? You think, okay, what's a shock absorber in the suspension system? You've got a spring, which is giving you the stiffness, and then you have a damper, which is going to stop the thing from oscillating when you hit a bump. The spring will deal with the suspension system will deal with the bump, but then the thing stops oscillating. And that's because you've got a dampening system, okay? Now notice there's a distinction between damper and dampener, or dampen system and damp system. Dampen means to make something wet, okay? Damper is what we're dealing with, not a dampener. Okay, so I'll move there anyway. Okay, anyway, so this is a typical example of what's known as a viscous damper, which deals with velocities, okay? And so you've got like I said, a piston with a cylinder full of oil. Okay, and within the piston there'll be some little orifices. Okay, so as you push the piston through, okay, there's going to be a thing, and we'll talk about dampers in a future session. But the oil from one side will have to pass through that orifice into the other side. Okay, and that orifice, that constriction, okay, is the thing that gives you the damping because it's hard work to push the oil through. Notice when this isn't moving, when it's constant, okay, there's no damping force at all. It's only when the thing's actually moving that you end up with the thing. So it's not like a spring, which when you push it, is going to try and push it back. Okay, when you push a damper, it's a bit complicated because you've got different areas that's actually going to expand. But like I said, let's ignore that bit. Let's assume it can compensate for the damage of the thing. But when you push a damper, it doesn't try and push it back. Okay, but when you move it, that's when it's providing the thing. So instead of it being related to the displacement, the damper is actually related to how fast you're moving the thing, okay? So instead of it being x and y, it's x dot and y. Okay, so when you've got in terms of working out a damping force, okay, you've got C, which is the damping constant, in Newton seconds per metre, times by, here we've got the relative velocity between x and y, between this end and this end. Okay, so when, it's interesting when you read articles about cars and with adaptive dampers and stuff and how, you sometimes see journalists talking about the fact that the car leans less when they've got hard dampers. But that's a fallacy, okay? Because the damper doesn't change how much the vehicle leans. That's all to do with the springs, okay? What is changing is how fast it can respond to those things, okay? And with a hard damper, obviously you can when you're doing transient things, you're going to get much stiffer suspension, okay? But the actual sort of lean of the suspension, the springs, aren't changing. It's what the damper's doing. Okay. Well, like I said, it's to do with the speed. Okay. So you get more damping when you've got a higher speed. There's some constant times for that. And obviously, adaptive dampers, if you've got a car with adaptive, what's changing is this value of C. Okay. And that's obviously changing the other thing. But the case, if you've got a passive spring, then that's not changing. Okay. So that's how I see the thing. So stiffer suspension. We normally think, okay, well, that's going to be a stiffer spring. Well, in fact, what they're doing is they're just stiffening the damper up, so you get a much more, the response to your inputs is more like solid suspension. But like I said, in fact, slow it down, and it's actually going to make much difference. So, if we were to represent this as like a very simple mass spring damper, you'll see MSD or max spring damper system all over the place in terms of dynamics, because like I said, that's the real system. And here we're not driving it, there's no force being applied, okay, and we can again write an equation associated with this model, okay. So again, sum of all the forces, okay, equals mass times acceleration, and notice I've also got a minus sign in front of the damping term. That's because this time we've got our mass here, we're saying x is positive this way, and we've got Fs plus Fd, okay? Going in the opposite direction. Because dampers, like springs, oppose motion. they don't want the thing to move. Then they're going to apply a force if you start moving it. Okay? That force, instead of it being based upon displacement, is going to be based upon velocity. Okay, so we end up with with mx double dot equaling the sum of the forces, which is Fs, which is going to be k times x, and Fd, which is going to be c times x dot in this case. Okay, because the dampers between the mass and the ground, obviously the only velocity there is x dot. Okay, because the ground doesn't move. And so you stick them in, the minus signs there, you put all the x terms on one side, and this as your second order differential equation. Now, like I said, it's going to go through a bit of derivation now, and I don't expect you to follow it completely, but again, we're going to try a draw function. Okay, this time it's also an exponential. We'll deal with what lambda does, because lambda, depending on certain values of the system, lambda might be complex or it might not be complex. So that could be, say, a mega bit, okay, but let's not worry too much about that. We'll just call it lambda for the time being. We're going to use that as our trial function. And so, going through the motions, if you take the first derivative, you get a lambda coming out, because you've got a chain rule. So there's our nice simple exponent, decaying exponential, okay? And do it again, you get another lambda out. I don't know where the A's disappeared, there should be an A in there, apologies. Typos. There should be an A in there, okay? So if you stick that into your mx double dot equation, okay? Stick that in. So when we had x double dot, we put this term in with the A, okay? Where's the A gone? A. You stick that in, okay? And then you put where the x dot was, you stick that in, okay? And then where the x was, you stick that in. All of the terms have this A e to the lambda t in here, so that can come out, okay? And this you can divide the whole lot by that, okay? So you end up with this. And this is known as when you're dealing with differential equations, this is known as the characteristic equation. Have you heard of that? Auxiliary equation is the other name? Yeah. This is a quadratic equation, yeah? You've recognised, you know that from school. Yeah? So x squared plus bx plus c equals 0. That's a quadratic equation. And obviously, what can we do with the quadratic equation? Well, we can find the solutions to the quadratic equation using the quadratic formula. I assume you recognise that when you've got x squared plus bx plus c equals 0, then that x1 and 2, x2, okay, is going to be, what is it? Minus b plus or minus the square root of b squared minus 4ac and 2a, yeah?
Yeah.
Yeah? A few years ago, when my daughter was much younger, she used to watch Peppa Pig. And Peppa Pig's Daddy Pig, does lots of things with numbers, okay, as you know. And there is an episode of Peppa Pig, believe it or not, where on the blackboard behind Daddy Pig, there is the quadratic formula. Okay, so they're surreptitiously teaching 2 and 3-year-olds about quadratic formulas. Interestingly enough. Anyway, so there we go. My daughter's now much older and doesn't watch Peppa Pig anymore.
Does she know quadratics though?
Indeed. Yeah, she's just dealing with fractions at the moment. So anyway, so you end up with the quadratic formula. Okay, so here's on c. Obviously was the bit in front of x. Lambda. Okay, so obviously that's minus c. So minus c in there. Okay, and then we've got our c squared minus 4km. Well, there's our b squared minus 4ac. And then over 2a, which is 2. And there's the plus and minus. Okay, because there are two values to that quadratic formula. Okay. Now, this is where the complex numbers come into it, okay? If c squared minus 4km is positive, then we've got a nice real number. When you take the square root of a positive number, you get a nice number, okay? If it's equal to 0, then it doesn't matter, you take the square root of 0, it's 0, okay? Doesn't matter, okay? If c squared minus 4km is negative, which for a certain case of oscillation it will be, okay, then you end up with a complex number. There's going to be a j times by some real number. Okay, you can swap it around. You can make it for, if it's negative, 4km minus c squared times by j. Okay, So that bit there will be real if that quantity is negative the other way around. Okay. So two real roots. If it's negative, then you get complex conjugate pair. Like I said, they often come in twos, complex numbers, and if those two are equal to each other, so it's 0, you end up with a situation where this is a quadratic formula is a parabola, isn't it? If the parabola sits, we've got a real line. Oops. If our parabola comes down and touches the real line and move off, that's the two real roots. Well, the two equal real roots. Okay, obviously, and that gives us two roots. Okay, and the complex number is actually up here. But like I said, we don't really know too much about that. But like I said, that gives rise to three types of damping. Okay, if we oh dear, I should probably plug it in. If we to make some definitions of some things, what's happened now then?
No, it died.
Yeah, so good. Stay there. Okay. So we make some different definitions. We define critical damping being when the damping is equal to 2m and make a naught or 2 root k. And then we also define something that is the damping ratio, which is a dimensionless number where you take the actual damping constant divided by critical damping, okay, and that will give you this value for zeta. Okay. Now, zeta. So basically, if you've got critical damping, if we go back to that discriminant, okay, 2 root mk. That's the value for discriminant, okay. So if we go back into this equation, if c equals 2 root mk, okay, obviously c squared is going to be 4 mk, which is that. So critical damping will actually be this case here. Okay. So that's the case when but like I said, often your damper will be less than critical, and in many engineering systems you have this situation where you've got what's known as C will be less than CC, and so theta will be less than 1. Okay, and that is what's known as underdamping or subcritical damping. And that, like I said, the reason why we focus on that is that most engineering systems are that, but I'll talk about it in a second. So, say the value of the damping ratio can be used to characterise the responses. You can rewrite those roots, okay? Ignore the equation 1 has that, okay? So if I go back to the equation for roots and make these substitutions, you end up with this situation, okay? And so, like I said, by characterising that value of zeta, okay, if zeta is 1 or greater, or if zeta is greater than 1, this number is real, okay? If zeta is equal to 1, then this number becomes 0. If zeta is less than 1, then this becomes a negative number, yes? Okay, so there's your complex and non-complex roots to the equation. Okay? And so what you end up with is a situation where when zeta is less than 1, you have an underdamped response, okay? When zeta is greater than 1, it's called overdamped, and when zeta equals 1, you've got something that's critically damped. Like I said, the other words for that would be subcritical, which is underdamped, supercritical, which is overdamped, and critical, which is damped. Okay. Now, the way these responses look when you actually start a system oscillating will be different various damper rates. With a system that's critically damped, okay, well no, let's start with the underdamped, okay, you get a system that responds very quickly, okay, but when it reaches equilibrium, it'll overshoot, okay, and then it will move back and it will overshoot again. So a bit like the free undamped system, okay, it will continue to oscillate, okay, but it will overshoot and continue oscillating, okay. But it obviously gets to that equilibrium position quite quickly, okay. overdamped means that it will take a long time to get to the equilibrium position and it won't overshoot, it won't oscillate at all. Okay? And the critically damped is the fastest way to get to that equilibrium position without overshooting. Okay? Now the thing is that this is probably undesirable generally. Okay? This is okay, but it's actually often you actually want to get to the equilibrium position even quicker. Okay, and you don't mind a bit of overshoot, which is where you get an underdamped system. Okay? Most engineering systems exhibit an underdamped situation, so that's the one we're focusing on. So we won't worry too much about how that responds. Okay? Underdamped is where it's at. And if you look at sort of car suspension systems, you've got a situation where you don't get something like this, okay, but you get something, where it overshoots just a bit and then settles, okay. And if you came to the tutorial last week, on Monday, then you would have seen me talking about that. So as we go, a mass spring damper system has an effective mass of 3 kilograms, okay. The spring stress is of 55 newtons per metre and a damping cost of 4 newtons per metre. What's the damping ratio? Okay. So remember, and the damping ratio. How you write this symbol is up to you, okay? As long as you recognise what it is, okay? I try and copy the way that's written in the notes, okay? I try and copy this value, this thing. But obviously that can look awfully like a 5 if I'm not careful, okay? So you've got to try and work out what it is.
Yes.
Okay, so this should be straightforward to do. We know the damping ratio is C divided by CC, where CC is 2 MK or KM. So we've got 50. What have we got? 4 divided by 2 root km. So 55. 3. And if you do that sum, that so 0.155. So my damping ratio there is constantly below 1, okay, so I've got an undamped system. 10.155. So if I take those roots of that equation, the complex ones, okay, so I've taken the j out and I've switched them around, okay, and I end up with this situation where I've got 2 exponentials, both in terms of j, okay. You can go through the motions, there's mathematics behind this, okay. It's a bit cunning, it's a bit complicated, and not really worthy of your time and attention, but if you go through the motions, this equation can be rewritten to be like this, okay. Where A is going to be an arbitrary constant, okay, because we find the initial difference as is alpha, okay. But like I said, this bit, this retains, that's here, okay. But this bit equals that, the real part of that equals exponential. Okay, so like I said, we're not going to worry too much about how we went round that point there. Okay. This is a mistake. This should be a D. Okay, that should be a D, not an O. Okay, so we've got an amplitude of oscillation. Okay, there's my oscillation, a cosine omega D times plus alpha. Okay, I'll talk about what omega D is in a second. And then this bit here, e to the minus something times by t. What happens when t is 0? E to the 0 is 1. So I've got my full amplitude. Okay, as t goes up, this value starts going down, and if t is big enough, this value is 0. Okay, and so you can see that my amplitude, I'm going to start out with a full amplitude, okay, and as the system goes in time, the amplitude is going to reduce. The frequency doesn't change. My frequency up front is the same as the frequency at the end. Okay, so if you're sketching this, make sure you don't slow down your frequency or speed it up even as time goes on, because that doesn't change. Now, what's omega D? Well, basically, when you've got damping, okay, the relationship between omega naught and omega D, you've got this thing here, okay, we call that omega D, the damped natural frequency. Okay, and the reason why you do that is the system, when you've got damping, clearly the energy's been taken out as it's trying to oscillate. Okay, and if energy is being taken out when it's trying to oscillate, I wonder if that's.
Hey, there we go.
Sketchy connections. When you're so when you're oscillating, energy's been taken out. It's trying to move backwards and forwards, and obviously if you're taking energy out, it's going to move backwards and forwards more slower than it would do if there's no damping. And so this thing moderates the natural frequency to become a damped natural frequency based upon the amount of damping. Okay, if damping's low, if this value is 0, then they equal to each other. If damping is high, okay, then this value is going to be quite a lot less than this. Okay, so that's basically the damped natural frequency equation. So there's another little exercise here. There's the equation you need to use. Mass spring damper system has an effective mass of 3 kilograms, a stiffness of 55, and a damping ratio of 0.2. What is the damped natural frequency? Okay. So what does omega D? Okay, so let's just solve this problem. It's quite straightforward. If I say omega naught, root k upon m, so 55 divided by 3. .2817. Okay, so omega d is omega naught 1 minus zeta squared. Okay, so I've got 1.2 squared okay. So the differential frequency you can see is 4.1952. So you can see it's a bit slower than the frequency. This value is obviously less than 1. Okay. Yep. Oops,
So much. Are you one of those houses that you when you just think the stage? Yeah. I was watching that.
Okay, so to get the hertz, you take your omega value and you divide it by 2 pi and you get the values of hertz. Okay. So if you were to plot this equation, okay, when it's correct, okay, that's a D, and you end up with a situation like this. So here the dashed lines represent the sort of boundaries, the decaying exponential bit, but the solid line is our oscillation, okay? And you can see that as time goes on, the oscillation slowly dies away, and eventually, like I said, it's going to be so close to 0 that we can't measure it being anything other than 0, okay? The dashed lines, like I said, represent this decaying bit, okay? So if you were to plot this, you get this line. If you plot the negative of that, you get this line, okay? And you can see, like I said, the oscillation. Here we're going to start at A, so in this case alpha is 0. Start at A and then obviously it goes down. And as time goes on, that A e to the minus something times by t term is going to squish it down to 0. Okay? The frequency of oscillation, omega d, like I said, that doesn't change as it goes on. Oscillation over here, okay, is the same distance and period as the oscillation up here. Now the x1, x2, x3, x4, like I said, is basically the way you can start defining the peak heights, and you can then look at things like logarithmic decrement and these sorts of things. Okay, but I'm not too worried about that. Okay? Like I said, there's definitions of how you can calculate the peaks and stuff. This is quite underdamped because you've got quite a lot of oscillations. But like I said, if you increase the damping, you can actually play with different values of that. And in fact, if you did the tutorial last week, we did look at that. Possibly, we've got time for me to load that up here. Okay, so like I said, we've got this time down here, displacement, and obviously the system starts at 0 and oscillates down. Okay, and like I said, if I type in here Okay, and then will that do it? I'm not sure. We'll see. If I change the damping. Oh yeah. Okay, so you increase the damping, you can see that the oscillations increase much quicker. Okay, like I said, if you want something that looks a bit more like a car damper, then we need to go slightly. Critical damping in this case is 200. But if I go for say 150, and I'll plot that as red, we have blue, we have black. Okay, you can see the black here. We've got so much damping that it decreases, just goes over zero at the bottom. There's almost no oscillation, and then you're back in equilibrium position. So, like I said, a car damper is going to have this sort of profile rather than something that oscillates. If your damper's shot, yeah, your dampers are worn out, then you're going to get something more in the available rewind. Obviously, what should be there is something like the back one, because when you compress the suspension, you want it to return back, but you don't want it to oscillate afterwards. Okay. But like I said, we don't want critical damping. I'm not sure whether the equation works with critical damping. Let's have a look at it. It might not work if I set this to be 200. Does it oscillate? No, you didn't work. Okay. Anyway, right. So the equation is slightly different for critical damping. Yes.
What would something like a rally car have? Because they always talk about damping and that being quite different to anything else.
Yes.
Because of the harsh environment.
Yeah. I mean, you want the dampers to be quite. Yeah. I mean, I think the dampers in rally cars, because depending on the environment, on the rally car stage, isn't it? Yeah. If you've got something that's very rough, then you want the suspension to be quite soft with lots of travel. But you don't, like I said, but you still want to quell the oscillations. You don't want if it goes over a jump, you don't want it to bounce. But obviously, it needs to soak up the things. I mean, because obviously with dampers and cars, okay, you've also got differences in the damping when it's being compressed compared to when it's extended. Yeah. So you have different compression and rebound rates and stuff. And rally cars will have things that are adjustable depending on what you want. Because you don't want a wheel to fall into a pothole, but you want it to be able to soak up a compression. So the compression and rebound will be that's where it's at. Okay. And there are lots of tuning that's enabled. In your regular road cars, the dampers are what the dampers are fitted to your cars. Certainly when you get to high-end motorsport things like the new GT3 RS, where you can actually adjust the compression rebound on the fly in the car.
Compared to Formula 1, you want very strong dampers.
Yeah.
Because so you want to make sure the car is top of the road.
That's right. But like I said, you actually want, you don't want, if you've got a pothole, you don't want the wheel to fall into it. So your rebound damping will be greater than your compression damping. Because you want to soak up the bumps, you don't want your wheel to fall into the bottom. So, anyway, right. Okay, so there's your damping. Just another couple of things. If I took my equation of motion, the one that was mx double dot plus kx, so cx dot plus kx equals 0, and I divide everything by m, okay, I end up with this equation, which is basically another form of the equation, and by doing a bit of a little algebra and various other things about what these things are, we end up with this equation, okay? That's known as standard form. And the real advantage of writing this equation in this format, if you've got an equation, like this, with values for m and k, and you divide the thing by m, you end up with this format, which can match up here. So if you know what the coefficient is in front of x is, you can work out straight away what the damping ratio is of the situation, okay, and what the natural frequency is. So for example, if I had, I don't know, well, let's go for the situation that I had earlier. So I had 3x dot plus, what was it, what was the damping in that problem? I can't remember what it was now. that was 55x equals 0. And I'm trying to remember what it was. What was the problem? Let's go back here. 4. There we are. Okay, so there's my equation. I divide everything by n, so I end up with x double dot plus 4 over 3 x dot plus 55 over 3 x equals 0. Okay, so I know straight away that omega naught is root 55 over 3. Okay, paste it on here. And I know that my 2 zeta omega naught is 4 over 3. So I know my zeta is going to be 4 over 3 times by 2 omega naught. Okay, and if I know what omega naught is, I can feed that in there and I'll get a value for damping ratio. Okay, so straight away, just from the equation of motion, knowing those 3 things, okay, I can work out, bang, this and this, just from the equation of motion. Okay. And that, notice, it looks like this, C over 2, that'll be mk, or C over 2 m omega naught. Okay? Well, that, yeah, that is that. Okay?